From the arc of a thrown baseball to the orbit of a distant moon, the universe operates like a machine. Heavy objects pull on lighter ones, locking them into a predictable clockwork of continuous motion. This top-down schematic illustrates the strict rule governing that motion. Planets closer to the center feel a massive gravitational pull, orbiting quickly to avoid falling in. But as you drift further out, the grip weakens, and planets must slow down to maintain a stable orbit. Gravity makes this inverse relationship an ironclad law of physics, codified over centuries by figures like Isaac Newton and Albert Einstein. Because this math works so perfectly here in our own solar system, we naturally assume it scales up. We expect the exact same equations to govern the largest structures in deep space. If you know the mass of an object and you know its distance, you can calculate exactly how fast it should be moving. Our entire grip on physical reality relies on that calculation holding true. But scale that math up to a spinning galaxy containing hundreds of billions of stars, and the calculation collapses. The breaking point happens here, in the sparse, quiet neighborhoods at the very outer edges of these galactic disks. According to everything we know about gravity, a galaxy should behave just like a giant solar system. The dense, incredibly heavy cluster of stars in the center should be spinning wildly, while the lonely outer stars should drift at a much slower pace. In the 1970s, an astronomer named Vera Rubin set out to physically measure the speed of those outer stars to confirm the math. This line graph maps her exact findings. The downward curve shows what established physics predicted, speeds dropping predictably as you move away from the center. But the flat line above it shows what Rubin actually observed. The outer stars weren't slowing down at all, maintaining intense speeds no matter the distance. Based on the amount of glowing matter we can see, there isn't enough gravity to hold on to objects moving that fast. The math crosses a physical threshold. At these speeds, a galaxy should lose its grip and literally tear itself apart, launching those outer stars into empty space. This discrepancy suggests that our current map of the universe is missing a massive piece of the puzzle. The math that works so well on a local scale seems to be hitting a blind spot when applied to the cosmos. Since galaxies clearly aren't exploding, the scientific community had to make a logical deduction. There must be an immense amount of unseen gravity acting as a net, holding these speeding stars in place. But gravity requires mass. To generate that much holding power, these galaxies must be packed with a massive amount of physical material that we simply cannot see. Scientists gave this missing material a placeholder name, dark matter. Figuring out what it is begins by proving what it isn't. It is not dead, burned-out stars. It is not hidden black holes, and it certainly isn't antimatter, which would emit distinct gamma rays when it touches normal gas. Its actual physical properties defy human intuition. Dark matter does not absorb light. It doesn't reflect light, and it doesn't emit it. It completely ignores the electromagnetic force, meaning it can pass straight through regular matter without so much as a spark. By tracking speeding stars, humanity deduced the existence of a ghost. It is a massive structural building block of reality that refuses to interact with anything, except by casting a heavy gravitational shadow. A logical deduction is a start, but science requires empirical proof. If a substance is entirely invisible to our telescopes, how can we prove it's actually floating out there? Take a look at this spatial diagram. It demonstrates a phenomenon called gravitational lensing. We have Earth on one side, a distant glowing galaxy on the other, and a giant cluster of invisible dark matter sitting right in the middle. Even though we can't see the dark matter, it has mass, and massive objects warp the physical fabric of space around them, pulling it down like a heavy bowling ball resting on a soft mattress. When light from that distant background galaxy travels toward Earth, it doesn't move in a straight line. It enters that invisible dip, and the light path is forced to curve around the distortion, smearing and bending the image like a funhouse mirror. Astronomers can point their instruments at these warped visual smears. By measuring exactly how sharply the background light is bending, they can calculate the exact weight and shape of the invisible mass causing the distortion. We don't need to capture dark matter in a jar to know it's there. We just map the colossal dents it leaves behind in the geometry of the universe. This data visualization illustrates the scale of those maps, and it reveals a massive deficit. For every 1 pound of normal, visible matter in the universe, there are roughly 5 pounds of dark matter. It severely outnumbers us. Cosmologists now recognize this invisible mass as the cosmic web. In the early, chaotic days of the universe, it was the heavy, dark matter that clumped together first, forming vast structural filaments. That invisible structure acted as a gravitational trap. It pulled regular gas and dust into its dense intersections. If that invisible glue hadn't forced the early gas to pull together, the friction required to ignite stars and forge solid planets would never have occurred. The visible material that makes up our cities, our bodies, and the burning stars above us is just a tiny fraction of reality. We exist as a mere byproduct, resting on an invisible framework we barely comprehend.